Lecture 6, Learning Objectives. To review the method of OLS, understand how we formulate models and test hypotheses using OLS, understand how we can assess if the model is a good fit model using diagnostic statistics, R square, goodness of fit, we'll discuss, the F statistic for overall significance of the model, and T test for the significance of the B's, the B1 and B2. Now we are extending the bivariate model XY to a multivariate model because we are going to have more than one explanatory variable. Like previously we discussed books read and the score, number of the years spent in studying versus your earnings. We are going to have one additional now. Multivariate OLS regression allows us to estimate and test models with two or more explanatory variables. Like the example we'll be carrying is petrol consumption, MPG, that is the miles per gallon. That's what we want to determine, and it depends upon two variables, two explanatory variables. First, the weight of the vehicle, and second, the engine size. So that's what we're going to do. Multiple regression with two explanatory variables, petrol consumption, that is miles per gallon, as a function, as a dependent function, which is driven by the vehicle weight and the engine size measured in horsepower. So our theory here suggests that a car that is bulky, has more weight, it will tend to have lower miles per gallon. Similarly, a car that has higher horsepower, a bigger engine, will have lower miles per gallon, or vice versa. So we expect a negative association, correlation between the variables connected in this function. Okay. Hypothesis testing. Hypotheses are derived from theory or from observation that leads to a hypothesis. This is absolutely true. Hypotheses are driven from theory or sometimes observations that lead to specific hypotheses. They inform our regression models. Yes, they help shape the regression models we use in our research. Suppose our research question is what determines firm sales? This is a search question that asks what determines firm sale. So we have the literature by searching the Web of Science database of articles published and the library catalog for books using keywords. So what we come up with, we find two distinct but related literature. First, a macro literature based mainly on aggregate sales for all firms over time. Aggregate sales for all firms over time. A business management literature based on sales of individual companies for a particular year or set of years. So we have either macroeconomic literature or management literature that shows you the sales of individual companies over specific years. Both have interesting hypotheses. Maybe sales depend on consumer income. If consumer have higher incomes, they will buy more of your products, so your sales goes up. Very simple one. But in fact, sales depend on many variables. Your sales depend on consumer income. Higher the income, higher your sales. And product characteristics. If your product has good characteristics, good features, your sales will be higher. If your marketing function is efficient and effective, you will have higher sales. And the number of close competitors, products, rival firms, if they are less, then you have higher sales. So there could be multiple factors that your sales depend on. So what we know that firm sales are a function of many variables. Your salesperson, interest rate in the market, disposable income, tax rates, your marketing function, number of sales employee hired, spending on advertisement, number of competitors, economic growth, and there could be many variables. But we are interested in the impact of marketing alone. For example, we decide to estimate a simple linear model that says that firm sales, S, depends on marketing expenditure, M. So we can estimate the parameters, the betas, using the following equation. That's what we did in the previous lecture, lecture 4 and 5. So this is it. S is B1 plus B2 times M plus E. Theoretical models and hypothesis testing. We should formulate a hypothesis. This is done by setting up a null hypothesis. What is a null hypothesis? Null hypothesis is a statement that there is no effect or no difference, and typically it is denoted by H0. An alternative hypothesis is a statement that suggests that there is an effect or there is a difference. So H0 says there is no effect or no difference, and HA, alternative hypothesis, it says it suggests that there is an effect and there is a difference that we are studying, and it is denoted by HA. A common convention for null hypothesis is that beta is equal to 0. Let's discuss further. So let's say, for example, beta 2, let's say this is our original equation. So hypothesis, null hypothesis, beta 2 is equal to 0. And alternative hypothesis, it's not equal to 0. If it's not equal to 0, it's either plus or negative. So it's a two-tailed test. So this form is very common, and it is used by default in our statistical package like SPSS, data. So when beta is equal to 0, that is suggesting that it's either positive or negative. Whereas null hypothesis suggests that beta 2 is equal to 0. Then there are some other examples that we can set up different hypotheses like beta 2 is equal to 0, null hypothesis, beta 2 is greater than 0, that is positive, that's alternative hypothesis, or beta 2 is equal to 0 and null hypothesis, that's null hypothesis, and beta 2 is equal to 1, that is the alternative hypothesis. Now look at this, what's the difference between the previous one and this one? In this you can see that these are no two-tailed tests, see, one directional only. So but we would have to tell the package to conduct a one-tailed test or a specific hypothesis where we want beta to be equal to 1 or greater than 0, or do it by hand maybe. So here we have the general form of a hypothesis. Null hypothesis, beta 2 is equal to 0, and alternative hypothesis, beta 2 is not 0. It could be positive or negative. So note that what we want to do, we want to estimate our beta. We want to estimate B1 and B2. So the issue is that the probability distribution may be normally distributed, but since we do not know the variance, when you don't know the variance, then we use a t-distribution. Remember, t-distribution approaches to normal distribution when n becomes larger, right? Remember, in previous example we did with n was 5. So clearly when n is beyond 30, then that t-distribution becomes a normal distribution. We discussed that previously. So using t-statistics for B1, the constant, and B2, the slope. These are the components of our equation. So how do we use it? T-statistics for B1, that is B1 upon standard error of B1, and same B2 is equal to, that is test statistics for B2 is B2 upon standard error. We will discuss as we proceed. So the important point here is with n minus k degree of freedom. What n here suggests? N here is the sample size or the number of observations in our data set. And what is k? K basically includes each coefficient being estimated. Like for example, here k is 2. It includes the slope of one explanatory variable and the intercept. Here k is 3. Intercept, coefficient of explanator W, and the coefficient of explanator HP, horsepower. We discussed this example a little while ago. Alright, so let's look again at our model to explain exam performance. We discussed that number of books and your exam performance, they are correlated. We develop a model. So in our simple model to explain exam performance, we had one explanatory variable, just number of relevant books read. The dependent variable, which this independent variable explained, was student exam marks, mean number of books read, determine your score in the exam. That's the model we've been discussing over the last few lectures. So this is the linear regression model we developed. Marks obtained is equal to B1 plus B2, books read plus E, and we initially took 5 observations. Now let us consider the data set with 10 observations. Still too few observations. So let's look at the results from SPSS. These are the number of students, number of books read, and the marks obtained. So basically we are concerned with this. So putting this in SPSS, the result is as follows. So this is the result generated by the model. So let us discuss them each one by one. Here, look at this. This is your B1, the constant, the intercept, 44.2. What it tells us? It tells us that if a student reads 0 books, their marks will still be 44.2%. And the B2 tells us that for every extra book a student reads, their exam marks increase by 4.8%. Right? So these are your two B1 and B2. So exam marks is equal to B1 plus B2, books read plus E, and we replace B1 with 44.2 we discussed earlier, and B2 with 4.8, and now we have our equation. Here we have our standard error. For constant is 2.128 and for books read it's 0.869. What these standard errors measure? Standard errors measure the accuracy of the coefficients, your constant coefficients and your slope coefficient in a regression model. So basically what they indicate the average distance that the estimated values deviate from the actual values. Then we have the beta, and what is T? We just discussed it a little while ago. So T for B1 is B1 upon standard error B1, TB2 is B2 standard error B2. Let us calculate there. So TB1 is equal to, you take 44, just like the formula, need to write it here, B1 upon standard error B1. So it's 44.2 divided by 2.128 gives you 20.767. For TB2, it's going to be 4.8 divided by 0.869, and that gives you 5.524. So these are the TB1, TB2 respectively. That is the test statistics for B1 constant and test statistics for slope coefficient book read. So we have discussed this. Now let us discuss R and R squared in detail. What do they mean? Now let's see how to interpret this output. So what you see here, R is 0.89. What is R? R is the coefficient of correlation. Remember, R is the coefficient of correlation that is range bound. It cannot be less than -1, cannot be more than +1. +1 means a perfectly positively correlation, and -1 means perfect negative correlation. R0 means the data set is uncorrelated. So what we have is 0.89, indicating that it's strong. What is R squared? This is interesting. Simply what you have R, just take the square. It gives you 0.792, or if you express in percentages, it's 79.2%. What it measures? First of all, it's called coefficient of determination. Coefficient of determination. It measures the proportion of variance in your dependent variable, our exam score, that is predictable from the independent variable. Let me give you a more relevant example. Let's say I established a correlation between my sales and my advertisement spending, and I determined the R to be 0.89, which means advertisement and your sales revenue, they are positively correlated, and there is a strong positive correlation. Fine. I would like to know how good fit it is. I take square of R, it gives me 79.2. It tells me that yes, sales vary, and 79.2% variation in sales is because of advertisement. It's a very interesting point. Please note. 79.2% change in my sales revenue is caused by advertisement. Then what about the remaining 20.8%? This could be because of other factors. Fashion, taste, trend, price of complementary goods, price of substitute goods, interest rate, tax rate, business confidence. It could be many other factors that can raise my sales level. But for now, what it shows here that sales and advertisement are strongly correlated, and the variation in sales that is explained by advertisement is 79.2%. In percent term, it makes more sense. All right. What about the R square adjusted? Basically, adjusted R square adjusts the R square value for the number of predictors in the model. Like in our example, there is one predictor, providing a more accurate measure when dealing with multiple predictors. Like in the example at the start of the lecture, we discussed that the miles per gallon depend upon the weight of the car and the horsepower. Right? So that's the idea. So it tells us how good is this model for explaining variation in the student's exam performance. So it says R squared provides a measure of goodness of fit for the whole regression equation. It measures this. We have already discussed this. This is important. R is range bound between -1 and +1. But R square, since it's the square of whatever you get here, it can never be outside this domain. Either it's 0 or it's +1, and that's it. Its value falls somewhere between this. So we need to discuss this. Adjusted R square here is 0.766. So the model is quite good at explaining, this number suggests that the model is quite good at explaining the variation in students' exam performance. More relevant books read, higher would be the exam score. Alright, next slide says the variation in the dependent variable y is given by y minus y bar squared and the sum of the squared. So the total sum of squares, that is the square deviation. Let me show you where. So here we can decompose the total variation in y or total sum of squares into two parts. First, the variation in the predicted value and the error, this minus this minus this plus this. So basically it has two components. The variation in the predicted value and the errors, which you call the random variation. So these two parts, variation in the predicted value and the error, the random variation. So we can call these two parts as the explained sum of squares, ESS, and the residual sum of squares, that is RSS. So total sum of squares is equal to explained sum of squares plus residual or unexplained sum of squares, and this is how it is represented statistically. The total sum of squares is equal to the explained plus the unexplained or the residual sum of squares. So here we have R square, which is the coefficient of determination, the criteria to assess the goodness of fit. It is defined by the ratio of ESS to RSS. Let me show you the next slide. So what our objective is, obviously we would like to locate the regression line so as to make the goodness of fit as high as possible according to this criterion. The question is, does this objective clash with our use of least square principles to determine B1, B2? The answer is no. This objective does not clash with the use of least square or whether we use this R square criteria. In fact, least square approach directly supports this goal, this degree of determination. So that's why this model ESS by TSS is exactly what improves the goodness of fit for the regression model. So hence using least square principle aligns with and supports the objective of maximizing model fit. So they both move in the same direction. So there is no conflict, no clash at all. So here we go. This slide shows you the reconciliation. There is no clash. To see this, we rewrite the expression for R square in terms of RSS, and that's what we get. So there is no clash. R square lies between 0 and 1. We discussed already. Other things being equal, the higher R square, the greater the explanatory power of model. I gave you the example of advertisement and sales. If R square is 1, then all the actual and predicted values for Y would lie on the regression line. In that case, RSS would be 0. That is residual sum of squares. So an adjustment is made to R square to compensate for the fact that as we add more explanatory variables, R square always increases. So this adjustment leads to an additional figure you see on SPSS output called R square adjusted. We just saw this a little while ago. What is R then? It is the square root of R square, the coefficient of correlation. Discuss this. It's a measure of how well the model predicts the observed data. And that's how it's calculated. That the correlation coefficient R is the square root of R square. Okay, now we have the last output generated by the SPSS, this one. Now this remains. The F statistic, what it measures. The F statistics measure whether there is a significant relationship between the dependent variable, our exam score, and the independent variable, the number of books read, the relevant books read. So basically, F statistics, it's a tool that we use to establish whether there is a significant relationship between X and Y or between dependent or independent variable in a regression model. So what should we expect? What score is good? Well, it is determined by its associated p-value. If the p-value is less than the chosen significance level, let's say 5%, right? If p-value happens to be less than the significance level, the relationship between the variable is considered statistically significant. Let us discuss these two in detail from the table below. The F statistic provides a test of the overall significance of the regression equation based on the analysis of variances, ANOVA. Okay, so here we go. This is ESS, explained sum of squares. This is the variability in the dependent variable, our exam mark, and explained by the model. Then residuals, unexplained sum of squares. This is the variability not explained by the model, and the total of these two is this. Degree of freedom 1, indicating that only one independent variable is involved here, and that is the books read, the relevant books read. And then this 8 here, the residual 8 here calculated as the total number of observations. They were 10, remember, there were total 10 observations minus the number of predictor 1, our number of books read, less 1. So it's basically the total number of observations minus 1 for the number of predictor. There is one predictor only, number of books read, and minus 1. So it gives you 8, and this is the sum of these two. Degree of freedom 9. Then what we have here, mean square. This is basically 460 divided by 1. 120.8 divided by 8 gives you 15.1. Okay. F statistic. How do you calculate it? It's mean square regression divided by mean square error. That is 460.8 upon 15.1, and it gives you 30.517. So this is a significant value. An F value of 30.517 in a regression model suggests a strong relationship between the independent variable, that's the number of books read, and the dependent variable, that is your exam score. So such a high value of F is likely to correspond to a very low p-value, well below the significance threshold. So confirming that the regression model is statistically significant and that the independent variable, number of books read, have a meaningful impact on the dependent variable. So what about the size, sign and significance of the estimated coefficients B1, B2 or the parameter? So let us discuss these one by one. Our B1 is 44.2. From where did we get it? Right here, which we previously discussed. Here, the output of your SPSS. So 44.2. So what this tells us that this high value indicates a significant baseline. Meaning even if a student doesn't read any book, still he is able to get 44.2% in exam score. So it is also understandable that there are other factors not included in the model, because a person who doesn't read any book still he gets 44.2%. So there clearly are some other factors involved. What about this number of books read? Every book read gets you 4.8% extra score. So each additional book you read is associated with an increase of 4.8% marks in the exam. Okay, then what we have is the standard error. This measures the accuracy of the coefficients estimates. Low value indicate more precise estimates. So you can say the books read, it has less standard error, so it's more precise, less precise. What about the standardized coefficient beta, 0.89? It shows there is a strong positive relationship between number of books read and the exam marks, close to 1, strongly positive. Okay, what else do we have? Then we have a T statistic for constant. So this is the value we use to test the null hypothesis that a coefficient is 0, I mean it has no effect. A larger absolute value, this much, indicates a strong divergence from 0. So the constant has a T value of 20.767 and the books read has a T value of 5.524. Both suggest that the coefficients are significantly different from 0. Look at these as well. So a constant has a P value of 0 and the books read has a P value of 0.001, and both of these confirm that the coefficients are statistically significant and likely to be impactful. So that's the conclusion so far. So our hypothesis is that the number of books has a positive impact on exam marks. That's what we have been doing and saying for many days in a row.
So more formally, this is it. Y is equal to B1 plus B2 X plus E. And more precisely, your exam marks is equal to intercept plus B2 times BR, books read, plus the error term, where B2 is greater than 0. So we set up a null hypothesis and an alternative hypothesis using the journal formulation. Thereby, our null hypothesis is that B2 is equal to 0. An alternative hypothesis is that B2 is not 0, it's greater than 0, a positive one, positive correlation. It's a one-tailed test because we're looking at just one side of it, not B2 is not equal to 0. In that case, it will be a two-tailed test. So in the case of two-tailed test, this is written this way. Just a little change. You put B2 is not equal to 0 rather than B2 is greater than 0. And that's what we have done. We have attained our estimate of B2. We calculate the standard errors and T statistics. We use the T statistics to test H0 and HA. But your software doesn't do this for you. It just print out the significance level, because it uses a two-tailed test by default. So if it passes two-tailed test, it will pass one-tailed test. So what are we looking for? The value and sign of the T statistics for B2. That is, the T statistic value and sign indicate the direction and strength of the relationship between an independent variable and the dependent variable. In our case, it's exam marks and the number of books read. We also need to look up its significance in statistical table. The significance of T statistic need to be checked against critical values in a statistical table to determine if the result is statistically significant. As a very rough thumb of rule, with large data set, more than 30, if the T statistics bigger than 2, B will be significantly different from 0 at the 5% level of significance. So for this, we should normally use at least 30 observations in OLS regression. So here we go. This we discussed earlier, that your coefficient of books read is 4.8, has a T ratio of 5.5 and significantly different from 0 at a significance level of 0.001. So at this value, we can be 99.9% certain that our estimate of beta 2, that is B2, is significantly different from 0. Here we have some instruction here. To transform it into confidence measure, we deduct 0.001 from 1 and multiply by 100 to get 99.9. Right? So these are norms for significance level and we should accept it. In management research, these are 1%, 5% and 10%, which means 99% certain, 95% and 90% certain. So therefore, we reject the null hypothesis and we accept the alternative hypothesis that B2 is greater than 0. We note that the sign of the coefficient B2 is positive. For every one book, you get 4.8% extra marks. So finally, a good summary. What do the B values tell us? So B values mean. B values tell us that the relationship between X and Y, whether it's positive, negative. If B2 is greater than 0, then an increase in X leads to an increase in Y. If B2 is less than 0, that is negative, then an increase in X leads to fall in Y. And they also tell us the size of the effect. Like for example, in our case, every one book read results in 4.8% increase in your score. So this tells us that if B is 4.8 positive, every one book gets you 4.8% extra score, and this is what I've been saying for many days ago. What are standardized B values? So far we have just discussed one explanatory variable. When there are multiple, then that's where we use standardized B variables. So standardized coefficients are useful when we are doing multiple regression. Like that example, your miles per gallon depends upon weight and horsepower of the car. So in this case, we have more than one explanatory variable, but these variables are normally measured in different units, like weight in kgs and horsepower in horsepower. So the standardized B value provide a way of standardizing the B's to make them comparable across variables. That's the difference. Then we have type 1 and type 2 errors, and they have been properly tabulated. In the next slide I will explain. Type 1 error. You reject a true null hypothesis. Null hypothesis was true, but you rejected it and you took a false alternative hypothesis as acceptable. So this is what you call the type 1 error. You reject the null hypothesis that was true and a false alternative hypothesis accepted. So occurs when we incorrectly conclude an effect or difference exists. Type 2 error. Failing to reject a false null hypothesis. When you fail to reject a false null hypothesis, you accept null hypothesis. A true alternative hypothesis is ruled out. So you do it in the opposite direction. We incorrectly conclude no effect or difference exists. So that's the summary.